Welcome dear learners. We are continuing Unit 4 Fundamentals of Analytical Chemistry. In the present module we are discussing Methods of Expressing Concentration Part 2. Contents of this module are normality, mole fraction, parts per million or ppm, parts per billion ppb, millimoles and milliequivalents, and problems based on these concepts. First of all, concentration of a solution. You are familiar with the concentration term in the previous module and some methods also in the previous module. Here we are considering the definition of the concentration of a solution just to revise the concept and to memorize the terms. The concentration of a solution refers to the amount of solute present in given quantity of a solvent or solution. In a binary solution, there are two components, at least one solute and one solvent. In such a solution, the concentration is referring to the amount of the solute in a given quantity of solvent or solution. In some units, we are taking the solvent, and in some other units, we are taking the solution. So, the solution concentration indicates how strong or dilute that solution is. For highly concentrated solution, the amount of the substance present in given volume or given mass will be high. For dilute solution, the amount of the solute will be low. Now, understanding and controlling the concentration of a solution is essential for accurate chemical reactions, product formulations, and analytical measurements. This point implies the fact that as the concentration of the reactant changes, the chemical reaction rate, the speed of the chemical reaction, the products of the chemical reaction, etc. may change. Therefore, an idea about the concentration of the solution is highly relevant as far as various chemical reactions are concerned. There are several methods for expressing the concentration of a solution, and the popular methods are just here once again for your reference, and the various methods for expressing the concentration of the solution are weight percentage, volume percentage, molarity, molality, normality, mole fraction, parts per million, parts per billion, and formality. Certain units we have covered in the first part, and in this module we are giving emphasis to normality, parts per million, parts per billion, etc. And first of all, we are considering normality. You study the two important concentration terms, molarity and molality. Similar to these two concentration terms, now we are having a new more unit, that is nothing but normality. Normality of a solution is abbreviated as capital N, is defined as the number of gram equivalents of the solute present in 1 liter of the solution. 1 liter means 1000 ml. So, in molarity we have discussed the number of moles of the solute. However, here we are considering gram equivalents of the solute. Number of gram equivalents of the solute present in 1 liter of the solution or 1000 ml of the solution. This normality is expressed in liters, gram equivalent per liters, or normal. The equivalence per liter is otherwise termed as normal. You know, in the case of molarity, the unit is mole per liter. Similar to that, in the case of normality, the unit is equivalence per liter. Equivalence per liter can also be called normal. So, a 10 normal solution means 10 equivalents per liter. A 0.5 normal solution means 0.5 equivalence per liter. 0.5 equivalence of the solute present in liter of the solution. That's why the normality is expressed in equivalence per liter. You can call it as normal. Now, normality n of a solution can be calculated by using this expression. Number of gram equivalence of solute divided by volume of solution in liters. Normality n is equal to number of gram equivalence of the solute divided by volume of solution in liters. Normality can also be calculated as normality n equal to weight of solute in gram divided by equivalent weight of solute into volume of solution in liter. This is because weight of solute in gram divided by equivalent weight will give you number of equivalents. You know, normality equal to number of equivalents divided by volume of solution in liter. So, in order to get to the number of equivalents of the solute, you have to divide weight of solute with the equivalent weight of the solution. That's why the expression for normality now changed to weight of solute in gram divided by equivalent weight of solute into volume of solution in liter. If the volume of the solution is expressed in milliliter, that milliliter should be converted to liter by dividing with 1000. On putting that 1000 in the denominator, in the final expression, that 1000 will appear in the numerator. So, the new expression will be normality equal to weight of solute in gram divided by equivalent weight of the solute into volume of solution, the entire quantity multiplied with 1000. This is very important expression for finding out the normality of a solution. Here the required data involves weight of solute, that is the given mass of